Yo, yo, yo. Let's see where we left off last week. Still working on the water. Have made a lot of progress in terms of the fluid solver in itself is the same, but how it is calculated and how it stores the data is different. It's now in such a way that we can actually use it later on in a good way. This one I wonder about though. One, 2, 3, 4. 0.5 gets fucked up. 6, 7, 8, 9. Okay, interesting. Okay, got some issues. I wonder if it's because we don't properly... But we clear everything, I think. Let's take a quick look. Clear water, previous, temporary, and water. Okay, this one I understand. If we add a small amount of water here, it will drain down there. But if we add a small amount here, yes. And this is weird as well. 0.2, 0.3. 0.2 gives us 15 water, 0.3 gives us 44. The fuck? Why? And then even less for 0.4, and then we go up, not down. Yeah, that one I want to get to the bottom of. We should be looking at maybe. If we were looking at 75 here, let's see. If we were looking at 75 water here, we would get Well, still. What is it? 128 plus 75. 203. I wonder. 0.5. 0.5 should give 128. At 0.5 water here, we should get 255. So we should be looking at roughly this, but we're not. This one doesn't seem to have the same problem. Here we have... Okay. We don't get the perfect values, but at least we get incrementally more water. That's beautiful. I wonder what's the reason. Maybe I know. So 0.1, 0.2, 0.3, 0.4, 0.1, 0.2, 0.3, 0.4, 0.5. Then we get this. And I wonder... Yeah, that's because we don't have the highest point, I think. What we get here with 0.5 is that the water overflows over this ridge here, and we start calculating downwards here, like how far can we reach without the water drying up. But unfortunately it dries up and we get a point around here maybe. So we get a point of around 14, or we can actually look exactly at what we get. We get a point at height 2, I think. Yeah, I think we get this point, and the water dries up here. So our calculation is, we take the height of this one minus the height of this one, and so we take that height over there minus this height, and we get water of 1 finally, and that's what we add. Third, this one. So by the same logic, yeah, it dries up too early here as well. 7.6, 7.8. 0.9, that's when we get the full fucking flow. And 0.1 screws us as well. It's a little bit weird. But this I like. So if we add the water here, we get, this one has the same height as this one, and then we get a downflow down here. But if we would, for instance, add the water here instead, that's our highest point now. So we get downflow here, and here we don't get anything. That's good. Do it like this. Yeah, so depending on where we add the water, we get different behavior, and I like that. What I don't like, however, is (0.2, 0.3). This one. probably gonna do... Let's see here. I want to fix this behavior, but we're gonna do another thing. So right now, the amount of water we can add goes between -1 and 1, and then we interpolate that between 0 and 255. I think I want to make it so that the amount of water we add is not a float, but rather an integer between 0 and 255. Because this is how I want it to. So if the player starts adding water here, it will gradually like continue add until the player cancels the action, and that's when we stop. So having results like this is gonna mess that up. Although what I can see here is this one I think I can explain. This one is a little bit... we can see here that with 0.1 we get a downpour here and a downpour here, downpour, downpour. And if we add 0.2 we still have those same downpours. But if we add 0.3 this one and this one is going to have the same amount of water, and we only get a downpour here and here and here. And the more water we add, now we removed this downpour as well. Here we didn't remove it, but here we did. Yo, what's up, Cooler SK? Hope you're having a wonderful summer so far. And the grass must grow and the water must obey. I agree, I agree. Having a few problems making it the water obey though. And now we have no downpours. Okay. Oops, I guess it makes sense. Quote, wonderful summer, yeah, sure. Is it too hot? This behavior we have here, I'm probably okay with it. Although, would love for it to never decrease. I wonder. So when we do cost to neighbor, yeah, cost base is 0. And we only have a cost for up. Which is as much as the height it moves up. I wonder, 0.1, 25, 0.2, 50. Here we should get 75, but we don't. Because 75, will it overflow somewhere? Don't think so. Actually, okay, I think it has to do with the fact. That we find another minima. So this one, we ordered them by height. And is it ordered by ascending? So we get the one with the smallest height. Okay, I get it. So here we get the one. So when we add 0.3 water here, we actually get this minimum. Okay, makes sense. Makes sense. Do we have the same problem here? Now this problem is the one I mentioned previously, I'm pretty sure. Okay. I'm pretty sure we want to take... I think we want to order them by distance to influx, and then by we just want to order them so the closest one, I think. Albane, may I ask how much experience you have within the professional industry? Because, bro, you're talented. I appreciate it. Thank you. When it comes to the professional industry with game development, I have 0 experience. Okay, so right now we ordered them by ascending, so lowest minima first, and then we just take that one and we fill it up. Depending on our cost parameters, we might get a minima that is further away, but it's lower. So I wonder... This one has always been a big question. So when we find all the minimas, how should we what is the term I'm looking for? How should we iterate them? Pretty much. And I'm still thinking, like, if we take a look at the minima part of the algorithm, so the code that actually finds the minimas, I'm trying to argue that we should be able to quit as soon as we find one. Like, we're always moving in the cheapest direction. I.e., we're always moving downwards if we can. So I'm thinking... probably remove this one. And I'm also thinking about, as soon as we get an add here, we just break. Either we break or we do is less than or equal to 0. But if this is the way we go, then we don't need to have this while loop at all. Because we're gonna find a minima, we're gonna add it, we're gonna break out of this while loop. We don't need to sort them or anything. And this one is always only going to be 1. So when we remove this one, we won't be continuing. Yeah, I think this might actually be... Let's see what kind of results we get from doing this instead. So, but this pretty much limits it in such a way that we can only find, when we add water, we always only add it to 1 minima. And I think I'm okay with that. Then we get this. I'm pretty much okay with this one, I think. It's gonna look a little bit prettier then. So we're gonna have a pool of water here. that has a very small overflow here, a diagonal one, and that overflow just trickles down here. This looks pretty good, I think. But this one sucks. I wonder about this one. It's pretty much like we... Yeah, it's weird, it's weird. But I think I know, so... Do I? Okay, so adding a lot of water to a plane point still takes a lot of time. This is beautiful. Albane, please tell me you will create a paid asset for Unity Marketplace with the terrain code when you're done to fund your amazing work. Appreciate it. Appreciate the kind words. I haven't really decided yet how I should share it. So the cell shader and the outlines are available on my GitHub. I was thinking of doing something similar with the terrain. But we'll see, we'll see, we'll see. Okay, the case with 0.5 here boggles my mind, especially since we had a nice overflow previously. I'm very interested in what happened. But okay, water 1, height 1. I think we stop at, as I said, some that is height 2. This one is height 2. Although I wonder why. Okay, height 2, height 2. We probably stop when we disperse from this one to this one. That's when we don't get enough water. But then again, so we just stop it much earlier. But then I wonder what happens at 0.6. What do we have here? Water 34. 0.6 times 255, 153 minus 34. So we're probably stopping at 120-ish, I would say. Do we have a height that is 120? $122, could it be? It could be that we stop when we walk here. I'm not really... Oh, that is unfortunate. Albane, possibly create a light version for GitHub and release the full featured one on the marketplace. Yeah, that's a good idea actually. I'm thinking about doing something similar with the outline as well. So the outline I have on my GitHub is the one I developed it a few years ago, I think, a couple of years ago, and it has, the one I'm using for this project has gone through quite a lot of improvements. So maybe like have the basic one on GitHub as I have now and this new one on Marketplace. And do the same with the terrain as well. Okay, so when it comes to this one right here, I'm pretty sure I know the problem. I'm pretty sure I know the problem, and I'm wondering, we could solve it by making the, like, by adding more constraints to the fluid solver. Or we could solve it by allowing for this kind of behavior. So if we add water here, it overflows here, and it might be possible for it to dry up here. Or we could also do, so the problem is it's down here, and in this case it's moving from here to here that screws it up. But I wonder, yeah, this one can move downwards, so I'm wondering, if we should calculate We only want it to be able to dry up if it can't move in any downwards direction. I think. So it's more specifically this one right here, I think. So we try to spread the fluid, but we don't succeed. So the question is, don't we succeed because we already have more fluid? Or do we fail because the point we're trying to spread to already have more fluid than we're spreading? Or do we fail because the fluid dries up? So if the one we tried to add the fluid to doesn't have any fluid, then it means that it dried up. So then we want to check why it dried up. If it dried up because the height difference is 0 and neighbor height is bigger than m height, then we do this and break. This is basically, we're moving above. We're basically overflowing m. I think. Yeah. But then we have this one as well. N height, lowest unreachable height. And this is, it's because of this one right here we get the result we do. So I'm wondering about this one. If I want to include it. And then we can do int highest point is equal to, let's put it at 0. And then when we have done this, we do if p height is bigger than highest point is equal to p height. And the thing we did with highest point is we take highest point minus m height and then we do the max of these two. So instead of just doing this, let's see, yeah, instead of just doing this, we also do new fluid amount is equal to, can we do int mathf max of this one and this one, I think. So fluid solver, the previous solution, we did highest point M. The only thing we do, if P height is bigger than highest point, then we change highest point. And then finally we calculate new fluid amount by doing highest point minus M height and lowest unreachable height minus M height, and we take the maximum of those. So now we have reintroduced highest point here. I wonder if that is enough. Yeah, we should be seeing, I think we should be seeing the water amount when we get to 0 here. It should be a little bit bigger, but I don't know how much. We'll see. Okay, here we get this one again. Here we get this one, this one, this one, this one, this one. Beautiful. That's beautiful. Okay. Yes, we get an overflow down here. That's pretty cool. I'm a little bit worried about what happens if I do this. Okay, it works. But it takes a lot of time. But yeah, I still want to support this, I think. So like this is a stable... This is a stable state I'm okay with. So we pretty much have a lot of water, and we have water running over here. When we alter the mesh later on, it's gonna look way better here. But so we actually get an overflow down here. I think that's good. What happens if you cover the whole surface? Right now, so our fluid simulator, if I add water here, we can add a small amount. Nothing happens because we try to spread the water, but we don't find any place where it can pool up. So we don't actually get anything. So we're saved from that. So the player won't be able to overflow the full map, so to speak. And the furniture here, it does not affect the water. Right now, at least. Okay, this is way better. Highest point. Slowly but surely we fill it. And I wonder how it looks here now. So if we go 0.1, 2, 3, 4, 5. And then we get a... I don't think we can fill it up anymore. Oh, we might actually get an overflow down here, worst case scenario. But yeah. So here we can see that if we fill up the water here, we will get a downflow here, 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 here. But if we fill up the water here, then we will skip this downflow and this downflow. That's pretty nice. Here we get an overflow down here. I'm okay with that. What's up, modding Minecraft? Is the water gonna have reflections in the future? Yeah, so right now this is just... we just have boxes representing the water right now. In the future we're gonna go crazy with the visuals of the water. It's gonna look real nice. We're gonna have movements, we're gonna have rim foam, we're gonna have the movement of the water is gonna be more if it's in a downward gradient. We're gonna have reflections, we're gonna have like the character will affect the water, so if we run in the water you will have effect from that and stuff like that. Beautifully designed, thank you. Hopefully the calculations aren't too resource intensive. Yes, that is the thing. We can see here that adding this water, what do we have? Step 1 prep took about, what is it? 2 milliseconds. Then we have find the minimus, extremely fast. Then we have step 2 prep here on 9 milliseconds. Then we have finding overflow limits. This one took, what is it, 72 milliseconds. And then we have setting final fluid amount, which took 10 milliseconds. So we're talking about... and then we also have one thing that we don't measure, and that's adding all of the visual objects, because we're not going to add visual objects in the final solution, so I don't time that one. But yeah, so look at this. With those included, we're at, what is it, 173 milliseconds, which is too slow for real time. But the idea here is we're gonna let a second thread calculate all of this, and then we're gonna hide that calculation in a nice animation. And anytime that second thread gets to a stable state in the fluid simulator, we will grab that result and we will visualize it. So, like, I think worst case scenario we set was like 2 seconds. That is even too much. But like, if all of this doesn't take more than 1 second, it's okay. We can hide it on a secondary thread. So yeah, I think the performance so far is okay. Sounds challenging. Yeah, I don't want to say too much, but I think like fixing the visuals of the water, reflections and stuff like that is gonna be, it's gonna be challenging for sure, but it's gonna be less challenging than it has been implementing this fluid solver, I would say. I don't know about that, Albane, but I appreciate it. Yeah, I'm actually quite impressed by it, but we can see the worst case scenario still. Look at this. This is, I think, worst case scenario, but I think we can be... Okay, so let's say that we add... Okay, this is worst case right now, and I'm okay with it because I think we're not gonna have this case later on. But let me show you this. So if we stand here on a total plane area, and I'm about to add 1 water, that is basically, I add a water value of 255. So the max amount of water is what I'm going to add here. And the algorithm will try to find a place in the terrain where the water can pool up. And look at this. This is going to be rough when it comes to timing, I think. So let's put it here and... Are you serious? Okay, still way better than I thought it would be. Find the minima 0.3 seconds. And basically what it does is... Let's see here. It searches through every point in this terrain, and we go in, what is it? Our cost is 10 by moving parallel, so I think we're searching an area of 10, 25, 50 times 50 points, I think. And that is like, that's the worst case scenario. But, or actually, I think we might have one case that is worse. Yeah, this one, definitely. Definitely. Mm-hmm. Yeah, here we have finding minimas is extremely fast, finding overflow limit extremely slow. 24 seconds, that's way too much. This one is way too much, and I think I know why, and I think we can fix this one. But okay, so this is our worst case scenario. Although I wonder. Yeah, let's look into this one. I think we can make it, or we pretty much have to fix this one, and I think we can. Modding Minecraft, I tried GLSL shaders before, and I was trying to render the classic monkey 3D object. Oh, Suzanne, I think she's called. It turned into 100 million pieces floating in the sky. Yeah, like it's a pretty steep learning curve, shaders. It's like you have to think about the problems in a different way as you would have, as opposed to as you would have on the CPU. That's basically it. But okay, so what happens here, and the case I want to fix, is that we add the maximum amount of water here. We search for minimas, and we find a minima here. And what I do now, currently, is that I take whatever input we had, the amount of fluid, I add that to that minima, and then we start a second search, which searches for... it searches for how much water we can fill this minima up with without it overflowing, basically. And the cost, one sec. And the cost for doing that is so the cost for moving in parallel during that phase is way cheaper than the initial phase, which means that I wouldn't be surprised if we pretty much search the full terrain in this case. And that sucks, but we can definitely fix that one. But yeah, this is also a non-problem, because what will happen actually is, I wonder. Yeah, we will find the minima, and then we won't add the maximum amount of fluid. We will actually add 1, I think, or 0.1. We will do the calculations with 0.1, then we will do the calculations with 0.2, and so on and so on. And I think we can do some very cool stuff. Like, we can hide a lot of these computations in the gameplay in such a way that the gameplay doesn't take any damage, if that makes sense. Yeah, I think we can fix this one. But how the water is supposed to use is that the player should go to the point where he or she wants water, and then we add it during a process. And for that, it works pretty good so far. So that's okay. Modding Minecraft is the game rendering with the CPU or the GPU. It's been an extremely long time since I've heard about any CPU rendering stuff. So we're rendering with GPU, and also the fluid simulation is done on the CPU right now. We're gonna look into that as well. I just need to run AFK real quick, and when I get back we're gonna look at some additional stuff we can do with this one. Absolutely correct, hide it in between the frame processing. Yes, we're gonna hide this shit, and it's gonna look amazing. And like, I'm almost entirely sure that we can hide it in such a way that it just looks like it's gameplay. So once again, like when we add water to a point, the player will go over there with a hose and start spraying water. And then we will just play that animation while all the calculations are done on a secondary thread, which shouldn't affect the frame rate too much. And that's about it. And that's probably what I want to do soon. I will see. I'm just gonna run. I need to run AFK real quick, and when I get back we will take a look at some of the things. Okay, back, let's see. Thank you, Albane, we trust in you. Thank you, appreciate it. Okay, so let's see, what do I think should be the next step? Yeah, we're gonna alter... I think I'm gonna alter how water is added first of all. Or actually... Okay, right now right now we reset everything, so when I add 0.1 again here, we just reset it and we get the same result. That's not really what I want to do. Instead, we want the previous result to affect the new one, so if we add 0.1 again, it's as if we added 0.2, right? I'm a little bit... Yeah, let's take a look at the full algorithm again. So like, behind the scenes we have a texture, and we work with that texture at all times. So we have 3 channels: water, water previous, water temporary. And all of those 3 are used during the algorithm. I think the first thing we do is we move whatever we have in water to water previous. Let's take a look instead. Okay, so first of all we clear all data. I don't think that's what we want to do. We move data, we move water into water previous, but we don't reset it. So this we're gonna skip. Water, water previous, and then we set data in water temporary. So that's the channel we work with. We spread the fluid to neighbors using water temporary. And that's everything we do here. Okay, so take what we have in water, put it in water previous, but keep water as is. And then we work with water temporary. And after that, we order our final points by height. We only have one here, so we can probably clean this up a bit as well. But anyway, then we alter the data we have in our channels, and this one is a little bit messy, and this one controls quite a bit of things actually. So alter data, what we do here is we want to alter this one using this one. And then we send in 2 anonymous functions. One that alters this one, and then one that alters this one based on this one and this one. It's a little bit of a mess, but it's basically this one is a function we apply to this one, and this one is a function we apply to both of these, and we add the result to this one. And right now what we do is we take water temporary, put it into water, but if we go through what we do with water temporary first, we do this. Basically, if the value in water temporary is bigger than 0, then set it to fluid amount, otherwise set it to 0. So for every data we have in here, we set it to fluid amount if it's bigger than 0, otherwise 0. And then the result we get from that, we take the max of that one and the destination, and that's what we set it as. I'm a little bit worried about, we want to do this in a different way. So as I said, I want to add. So we basically want to add what we have in water temporary to what we have in water. I'm still going to do this one. So when we find the minima, we actually disperse water. So when we finally find the minima, we might find, like if our initial water amount is 0.5, we might actually just find the minima when we have dispersed so much water that the final water amount that reaches the minima is 0.1. But since we have a continuous influx of water, I want to set it to fluid amount. So if we find the minima, the fluid amount at that minima should be our influx of water, basically. And this is also the thing that in our worst case scenario, the cause for our worst case scenario taking 20 seconds was this one right here. But anyway, I'm thinking of doing so S and D, I'm thinking of doing return mathf clamp, and here we do S plus D, but we clamp it between 0 and 255. I think. And once again, this is the water we change. So when we have done this one, we take whatever we have in water and we put it in water previous. And this one, we also reset source here, which is eventually going to be wrong, because I have to specify this as well. When we visualize the water in the world, it's always going to be whatever we have in the water channel that we're gonna visualize, and this might screw it up. Or this one might screw it up. So what I think we want to do yeah, we did this because later on we want to do this. Okay. Okay, actually this might be okay, because what we do here is we move data we have in water to water previous, and we reset source. So we reset this one, but move data also has a fourth parameter, that is apply, and by default apply is false. So by default we don't apply these changes to the GPU, so we might still be able to render it as it was. But I wonder, water temporary. I think by just doing this instead of max, I wonder if everything else is good. Once what previous, yeah, maybe. Let's try it. So if I add 0.1 water here, and then I add 0.1 water more, nothing happens. Okay. Okay. Let's see, water 0, 0.21, 0, 0.191. Okay, we're missing one step. Mod in Minecraft lol, the bed just smashes into the ground every time the game loads. Yes, indeed it does. Just want to see those nice physics every time I start it. Okay, so what I'm worried about is how do we end? Okay, so when we end this full thing, we have our result in terrain data type water. Okay. Finish step. So we have our result in water. That's good. We show it. So what I want to do is I want to do clear data water temporary. Yeah, I think that's pretty much all we want to do. Yeah, unfortunately I can't take any credit for the physics. It's just the Unity default-ish physics. So yeah, it works very nice. There we go. Okay, there we got screwed. I wonder why though. Water 27, water 5. Why do we have water previous? Water previous, okay. Do I need to clear water previous as well? 71, 91, 63. Why? 81, 99, 104. Interesting. Yeah, I'm pretty sure when we get to this... $107.27. Interesting. Like, it should be the equivalent of doing this, basically. But it's not. So, the kind of result I want to see is 0.1, 0.2, 0.3-ish. But that's not what we're getting. .1. Okay, it's what we're getting here. That's beautiful. Okay, I think I know. Finding overflow limit 27. Yeah, we get a new overflow limit, and this limit sucks. Thanks to this one. pretty sure it's because of this one, unfortunately. Yes, it's because invalid end nodes. When we do this, I think, let's see here. I think we want to add some additional constraints to this one. Like I mentioned earlier, so basically this is, we're moving in parallel and we can't add more fluid, which means that moving in parallel, or we're moving in, so this happens when we move in parallel and the fluid dries up. And I want to quit if that happens. The first time it happens, but only if we haven't already moved, or only if like we have okay, I want to quit here, but only if one of these neighbors is not going downwards. So I want this to happen only when the fluid dries up, because it can only move in parallel or up, basically. And this gets me to another thing we're gonna do here to both improve the performance and remove some repetition in this code. And I'm talking about this tuple here. So we use tuples throughout this algorithm, and right here we create a new tuple, and if I've understood this correctly, this is by value. So when we do this, when we set the x parameter in this tuple, we're basically creating a new tuple. Same here, and then same here when we call this one. So we basically create 1, 2, 3, 4 tuples, which is just some unnecessary garbage. So I'm gonna create a method that returns a list of tuples like this. So we're going to create a method that returns all the neighbors of a point. And we might also sort them, actually. So let's see here, can we make it... Okay, let's do it like this. Private list or array. So can we do it like this? Terrain patch get neighbors let's do it like this. I think we're gonna start with a list here because we're gonna fill it up of tuples. Neighbors. And then we're gonna have this. Wonder, okay, so increment x by I, increment y by j. Then we want to get index wrapped as well. And then I don't think we want to use this one here. Get terrain patch. I think we want to do this one. So, I think we want to do terrain patch p.terrainPatch.get terrain patch unsafe x plus I, or actually p.x plus I p.y plus j, and then we do if terrain patch is not equal to null. And that's when where we're going to create our tuple. And we're going to do neighbors add. And we want to add terrain patch, and then the x and y is terrain patch.get x, get index x wrapped p.x plus I, and terrain patch get index wrapped y p.y plus j. I think this is the one we want to add. So yeah, then we add them to neighbors, and finally return neighbors. And here I think I want to order them order by ascending. And dot terrain patch dot get terrain data dot get data height, and then to array. So now we have a method where we get all the neighbors given a point represented as a tuple. A tuple has, in this case, has a terrain patch and an X and Y index. We create a new list for all the neighbors, and then we loop through all the neighbors in a grid. So 8 neighbors. -1, -1, 2, 1, 1. And then we try to get the terrain patch given the offset in index. If it's null, we don't do anything. Otherwise, we add it with terrain patch and the indices wrapped. And finally, before we return, we order them by, so we get the neighbor that has the smallest height first. And I do this because I think we can simplify some of the checks later on if we do this ordering. But then again, I wonder, I think we can also do bool order by height is equal to false. And then we make this one return a list instead. And before we exit it, we check if order by height, or actually we can do this. Return order by height if that's true, we return this one, otherwise we return neighbors. Yeah, we need to do 2 list here. I think I want to do this. So we get all neighbors and we have the option to get them ordered by height. Okay, let's see how we can clean this up then. So for each I want to do a for loop here. Int I is equal to 0. Do I? I think I do. get neighbors of P, and in this case true. So get neighbors and order them by height. The reason for doing this in a for loop instead of for each here is because I want the index, because if we end up, let's see. Oh, it's actually down here later on I want to do it. Because if we end up in this one, I want to check if it's the first object. If it's the first neighbor, then we know that the first neighbor has a height that is equal to m, so we don't have any neighbors that goes downwards, and we can exit. Yo, what's up, Geralt? So up here we can actually we can skip this one here. So, but we're gonna have to do it later. So for each n in get neighbors. The fuck? P. Okay, so we can't use it here because of this one. Why? Okay, let's do this as well. Okay, so what is so wrong here? Finish step. Do we have... There we go. So instead of doing this, we can just do this. A little bit nicer. Let's see here. So get all neighbors. We get the height. We calculate height difference. We calculate cost. Spread fluid to neighbors. And then we just do this. Yeah, this is probably true. This one we don't do anymore. Okay, I want to clean this one up as well. In this case, I think we need to do it with a indexed for loop. So var neighbors is equal to get neighbors of P. And in this case, I also want to order by height. Okay, like this. And we don't need to do this. This one, however, Yeah, let's keep that one. Neighbors. Do I want to... Yeah. Like this, and let's see here. Yeah, better way to exit, question mark. Now we have a way better way to exit. Previously we had nested for loops, so simply doing a break here would only exit the first for loop and we would continue. Now we only have one for loop, so we might as well break. With the previous implementation, we might have exited the for loop a bit earlier here, but that also resulted in the problem we're trying to solve right now, this case. So I don't think we lose too much by doing this. Okay, and then we're in the final step, and we can simplify this one as well. But here we do for each again. Rn in p get neighbors p. Oh no. Yes. Is it though? So it's this one. Or actually, is it? I wonder. Or actually, I think we can do it like this. I think there exists C# for each with index. Really? Yeah, I don't want to do this, I don't think. Okay. Do I want to... How ugly would it be to do... Yeah, we want to... Yeah, no, we want to rename this one, but... I don't know. A little bit perplexed by this, since we define it in this scope. Ah, is it because this one actually? Yes, probably. Yeah, okay. So we have this, yes. Okay, so right now we haven't done anything differently, or that's what I'm hoping for. Let's run it real quick and see if we have the same result still. Also want to see what kind of timing we get, but yeah. Pretty quick. Okay. Okay, it works exactly as it did. I think we can see it by this one the most, yeah. And this, the issue we're seeing here, is hopefully what we can solve now when we have reordered the code. Jerry Dev, hey, would it be okay if you can teach me on stream? You can get a content. I got good experience in Unity. I don't really have the time for that, unfortunately, but good luck. Like, you're free to watch whatever I'm doing and learn from that. Eventually, it's pretty far in the future, we are going to develop some AI stuff here. Not enemy AI though, but like AI. But yeah, okay, so what happens in this, why we're getting lower here, is because we overflow over this ridge here. The water travels down to this point, and here it dries up. And depending on how it dries up, we calculate a new fluid amount, and that fluid amount is less than the previous one. And now with the restructured code, we have enough information to solve this issue. So like, we don't want to dry up if we only want to dry up the water if it moves in parallel, and it can't move downwards. But that is something we're gonna do tomorrow, because I gotta run now. Yeah, I've been doing short streams for a while now, been quite sick, but hopefully this week I might add another hour or two, but we will see. But yeah, thank you so much for watching, everybody. Appreciate it. Good progress today, and have a great rest of the day. Peace.